This here is the form of the Navier-Stokes equations that you usually see in physics and engineering journals and books. This is a form which you usually see in mathematicians and maybe theoretical physicists papers and books. This is a very interesting way of representing this equation. The main difference here is that the time derivative of the velocity here is presented in a simplified way. So this means the exact same thing as this here, but you have a more economical notation. The terms here on the right side are pretty much the same, but those equations are only valid if you have this conservation form. The divergence of the velocity field equals 0. This means that if you have the conservation equation, or better, the continuity equation, that the divergence of the density times the velocity vector here, this means that if the density of the fluid is constant, the time derivative of the density is equal to 0. So there's no variation, so you're left with the divergence of the density times the velocity equals 0, and this implies that the divergence of the velocity vector equals 0. If that was not true, the density would not be constant, and you would have to have the derivative of the density here. So you'd have a compressible fluid, and the compressible fluid is a very different thing. This, as usual, is the body forces or external forces per unit mass, and this here is the Laplacian term. So delta here means the Laplacian. Those two equations are the same, and this here is the viscosity term, the kinematic viscosity, which is the dynamic viscosity over the density. If the viscosity goes to 0, this here goes to 0, and then you have the Euler equations and not the Navier-Stokes equations. The interesting part here is that this convective term here can be represented in this notation. So what we have to verify is that this term here, it's equal to this term here, the divergence of the vector product of the velocity. But is this the same? Well, actually, if this is true, we can verify that it is the same. First, let's take a look at this term here. This term here can be written as the dot product of the velocity vector times the del operator, this all multiplied by the velocity vector. This is the velocity vector in Cartesian coordinates, and this is the del operator in Cartesian coordinates. When you take the dot product of both of them, what you have is, if you remember the properties of the dot product, you have that if you have equal terms, this is 1, and if you have different terms, for example, I dot j, this is 0. So we're left with this term here. The components u, v, and w times the partial derivatives. Each component times multiplied by the corresponding derivative in that direction. So u dx, v dy, and w dz, the respective components. So this here, this part of the term, now all you have to do is to multiply this again by this term here. And what we can do here is just use the distributive property. Using the distributive property here, the unit vectors here are conserved, so they did not disappear as in the case of the divergence. And expanding this term by the distributive properties, you are left with 9 terms here. U times dx, du dx, u times v dxj, and so forth. So now we have to show you that this here is equal to the divergence of the tensor product. First of all, what is this tensor product or this outer product? The outer product of these two vectors here is going to be a second order tensor. And you can easily prove this by writing the two vectors and doing the multiplication of these two vectors. It's not a traditional vector multiplication, but it's done in the way that you have 9 components here. So this here will translate to this term here, and now we have to apply the divergence to this outer product, to this tensor product. It happens that applying the divergence term to a second order tensor, you get a vector. And this vector here will have 3 components. This sum here, and this sum here. So you actually will have components in I, J, and K. So this here is the component in I. This is the second one is the component in J, and the third one is the component in K. There's 2 ways of interpreting this. There's some books that will mention that in this case here, in this scenario, the divergence represented by the del operator and the div operator are different things, because applying this expanded del product here in this case will result in this result, because they will be applied by columns here, and the other will be if they are applied by rows. So could apply this row by row, and you could apply this column by column, and this will be represented by these 2 different notations. But what happens here is that actually this tensor is symmetric. And because this tensor is symmetric, the 2 notations will give the same result in the end. What we mean by this tensor being symmetric, we mean that VU, UV. So the corresponding terms here are equal across the diagonal of the tensor. So WU, UW, WV, VW, and at the diagonal here you have the equal terms UU, VV, WW. So the result would be the same because of the property that this tensor is symmetric. So now if we expand these derivatives here, so you can use the product rule here. This will be U du dx plus U du dx. You could actually, this is actually 2 U du dx, but it's convenient to express like this. Likewise, this can be written as 2 du dy plus U dv dy. So we expand this term by applying the product rule. So now this first row is in y, in I, the second row is in k, in j, and the third row is in k. We can group here similar terms in u so that we can isolate the u terms here in these forms here, So, oops. So we can isolate the U term here, so you can group this term here. And you do that in each row. And it happens that if you have an incompressible flow, the divergence of U is equal to 0. So the continuity condition here will give us the divergence of the vector U 0. So this here is equal to 0. So this vector here can be simplified by making these terms, those three terms, 0. It can be simplified to this. And now we can, instead of writing this as a vector, you can write this as a sum. So each term here it's multiplied by y, each term here is multiplied by j, and each term here is multiplied by k. And expanding this, we will get at the same form as if we were expanding this u dot del u term. So this shows that under the continuity condition here for an incompressible fluid, the divergence of the outer product of u or the tensor product of u is equal to this notation here, u dot del u.